Somebody sat down with a stopwatch and asked a production AI the same boring question a few hundred times. The task is almost insultingly simple. Take a random number, bury it near the start of a long block of text, and ask the model to read it back. Same question every time. One variable, and one and only one. The padding. A little more filler between the number and the question on each run, so the model has to reach a little further back to answer. For a long stretch, nothing happens. The tokens come back at a steady rhythm. Then, at one specific prompt length, the whole thing slows down. Not a drift, a step. So, they hunted for the exact edge, narrowing by halves, and landed on a number. 131,042 tokens. Round that off and you get 128,000, which if you've spent time around these systems is a familiar looking number. So what did they actually just learn? Because the honest answer is stranger than the one you're expecting. Start with why there's a clock at all. When you talk to one of these models, the words arrive one piece at a time. That's a design decision. Generating a full answer takes real time, and staring at a blank screen for 8 seconds feels broken, so providers stream the output as it's made. It's the cheapest trick there is for making a slow system feel fast. But if the tokens arrive as they're made, then the rhythm of their arrival is a pulse coming off the machine that made them. The hardware stays hidden, and you get to take its pulse anyway. And that pulse isn't flat, because nobody serves these models the naive way. Running the full model for every token is expensive, so the industry leans on optimizations, and one of the most common has a wonderfully suspicious property. It's called speculative decoding from a 2023 paper by Levithon and colleagues. Alongside the big expensive model, you run a small cheap one. The small one guesses the next few tokens. The big one then checks all those guesses in a single pass. If the guesses were right, you just got several tokens for the price of one. If they were wrong, you throw them away and fall back to normal speed. So the system's pace now depends on whether the small model is guessing well, which means the pace depends on the content, which means the pace is carrying information. The exploitable part is that small helper, the draft model, which is usually built with a shorter memory than the big one. It's supposed to be cheap, and the long context window is expensive. Picture what happens when the answer lives further back than the small model can see. It's guessing the next token in a sentence that hinges on a number it cannot reach. It guesses wrong, over and over. Every guess gets rejected, the speed up evaporates, and you're back to the full price of the big model. That's the step. A small model going blind at the edge of its own memory. And the length where it goes blind tells you how far that memory reaches. So that's the mechanism on paper. They tested it somewhere where they could check the answer against something known. They built the setup themselves on a single graphics card. A 13 billion parameter model doing the real work, a 1.1 billion parameter model doing the guessing. Same padding experiment, and they got the same step. Then they switched speculative decoding off. The step vanished. Remove the mechanism, and the signal dies with it. That is what a causal test looks like, and it's the strongest result they have. And their estimate from the timing data came out at 2018 tokens. Context windows are almost always powers of 2, so round to the nearest one, 2048. That is exactly the real context window of the small model they were using. They didn't look it up. They timed it. Now, before you let that land too hard, this is one preprint, put up in July, nobody peer-reviewed, and nobody outside the group has rerun any of it. I'm covering it because it's unusually checkable. The setup is published, the ablation is a single switch, and it predicts a number you can go look up. So inside those bounds, the method works. In a room where you control everything and already know the answer, a stopwatch reads a specification off the machine. Then they aimed it at a box they couldn't open, and the stopwatch hit a wall. With Google's Gemini flash models, There was no switch to flip. They got the step. They got 131,042, and 2 models in the family returned the same figure. That's a real measurement, and it is genuinely consistent with a draft model whose reach ends right around 128,000 tokens. But consistent with is not the same as identified. From outside, they can't disable anything. They can't rule out that very long prompts get batched differently, or routed to different hardware, or hit a different caching policy, or trip a different attention kernel at some length threshold. Any of those would also produce a step. The paper's honest position, and mine, is that the signature is there and the cause is a hypothesis. And nobody outside this group has rerun that particular measurement. The paper trail is worth reading precisely. The researchers told Google in November of 2025. Google acknowledged the report the following January. Acknowledged is doing careful work there. It means a message was received, not Google confirming what's under the hood. Nothing public has been said since, as far as I can find. None of this is a new kind of attack. Back in 2024, Carlini and Nass showed that timing on these systems leaks. Watching encrypted traffic to production ChatGPT and Claude, they could tell specific messages apart and infer what language you were writing in. Around the same time, Wei and colleagues built a side channel specifically out of speculative decoding, using the number of tokens per round and packet sizes. They used it to fingerprint which question a user had asked and, in their own test deployments, showed the same channel could pull content out of the data store the system was using to make its guesses. So the channel was already known, and it was never only pointed at users. Server-side content was already shown to be reachable this way. What's specific to this paper is narrower than that. The shape of the model itself and how it's deployed, read from token timing alone against a production API. Which matters because the second half of the paper is where the abstract reaches further than the results do. That second attack goes after the model's shape, how many layers it has, how wide it is. The logic is reasonable. Different architectures produce differently shaped timing curves, so build a detailed model of how transformer math turns into microseconds, then search for the configuration whose predicted curve best matches what you observed. The abstract says the near-correct configuration lands in the top 10 guesses more than 90% of the time. I went looking for that number in the paper. It appears exactly once in the abstract. The tables do carry real results. There are controlled experiments where the method genuinely narrows the search with a success criterion the paper spells out. A guess counts as a hit if it lands within one step of the truth, one layer either way, 128 either way on the width. What the tables don't carry is that 90%. No table reports it, and the paper never shows how it was computed. Then there's one test against an actual remote service, searching for both at once across 2,068 candidate configurations. A near miss came 8th. The true configuration came 28th. So the second attack is real, and it's fenced in on every side. It assumes you already know which graphics card is running the model and have timing data from that same hardware to calibrate against, which is a lot to already know about a system you're supposedly reverse engineering. The paper is free, and those tables are a few pages from the end. Go see what's in them and what isn't. Subscribe if you'd rather I did the looking. So what do you do about it? The paper offers 2 options and doesn't pretend either's good. You could make every token take the same amount of time, the worst case amount, which the authors say would defeat the purpose of inference optimizations entirely. Or you could buffer, holding tokens back and releasing them on a fixed schedule, which they know may be impractical and can degrade quality of service. They close by calling a defense that costs neither latency nor user experience an open and difficult problem, which is a much more modest claim than unfixable. There's one more table, tucked into an appendix. They tested 14 remote services this way. 3 showed the signature, all 3 in the Gemini family. Everything else came back quiet. ChatGPT, Mistral, Cohere, Perplexity, the fast inference providers, and 3 other Gemini models. And the authors are careful about what that silence is worth, which is almost nothing. Their method produces false negatives. If a provider's helper model happens to have the same memory as its main model, there's no edge to fall off and no step to find. The attack quietly fails, reports nothing, and looks exactly like a system with nothing to hide. Which leaves a very small thing to know. 3 services out of 14 showed the slowdown at all. Everything past that, what's running, why, and whether anybody else leaks the same way, is still a closed box with someone standing outside it holding a stopwatch.